Okay, so we'll continue on in chapter 4. And so we've covered correlation, which is a numeric summary, just a value R to summarize or quantify the direction and strength of a relationship. And now we'll cover linear regression. Okay, so linear regression is now working towards creating an equation. And try to create a linear equation to summarize the relationship between the x and y variables. So correlation was a number that gave us, that quantified the direction and strength. Linear regression will create an equation that summarizes the relationship. It can also be used to make predictions for y based on x. Okay, the linear regression equation can also be used to make predictions of y based on x. Okay, and so generally we kind of give names to these variables. Okay, and so the x variable goes by a few names, and so does the y variable. Okay, so the x variable can be known as the explanatory variable, the predictor variable, or the independent variable. Okay, the y variable might be called the response variable, the predicted variable, or the dependent variable. Okay, and the idea is we use the x variable to make a prediction about the y variable. Okay, and because we do this, it's sometimes tempting to say that changes in x cause a change in y, but that's not the case. A correlation does not equal causation. Okay, it could be tempting a change in x causes a change in y. Okay, but that is not true. Okay, correlation does not mean causation. Okay. All it means is that a change in x is associated with a change in y. Okay, we can say so that's what we've got going on here. Okay, and so when we create a linear equation, okay, you can think back to algebra and how would we write the equation for a line? Okay, so from algebra, the equation of the line is y equals mx plus b. Okay, and here we said m is the what? Slope, and b is the y-intercept, right? Okay. In statistics, it's similar. Okay. And we would say y hat is a plus bx. Okay, and so now b is the slope, and a is our y-intercept. Or we might just call it the intercept. Okay, and we put a hat over the y to indicate that this is our prediction for y. Okay, so this is called y hat, and this is the prediction for y, not the actual y. Okay. So yeah, whenever you see a hat over something, we'll see later on in the course, we'll see hat, p hat versus p. It just means that it's a modified, it's something related to that letter, but not the actual variable. So it's not y, but it's something related to y. It's our prediction for y in this case. Later on, we'll have p hat, which is not the actual p, but the p coming from our data. So that's what we have. Okay. So to explain the concept of linear regression, we'll have this ongoing. We'll have this example. If I may flip the slide. Okay. And what we're going to do is we're going to look at a book. Okay, so we look at a book. And what we're going to do is we're going to count how many pages are in the book. And based on how many pages, we're going to try to predict the width of the book, or how thick the book is. Okay, so we look at the number of pages. Okay, and then we will try to predict the width of the book. Okay, so you can imagine you've got some book. Okay, and we want to know kind of how wide is the book. Okay, so this is the width, and we're going to just look at the number of pages. So what is our x variable and what is our y variable? Okay, number of pages would be what? X. Okay, so x variable is the number of pages. And what is our y variable?
So what is
the width of the book. Okay, and so in the form, we've got y hat is equal to a plus bx. We're going to have width hat, or we might say predicted width, is equal to a plus b times x, and x is the number of pages. I'm just going to write pages here. Okay. Or I might, I'm going to just plug in values here, and so we've got 6.22 plus 0.0366 times pages. Okay. Okay, so we'll just say, you know, these values, the values 6.22 and 0.0366 just were provided in the book. Okay, so we can also write it this way and just say the predicted width is equal to 6.22 plus 0.0366 times pages. And this would be a linear regression equation, and let me create like kind of a thing. We've got pages here. And we've got width. Width is measured in millimeters, and you know, we just have some kind of trend line here. And that's what we have. Okay, and so what we can do is we can say, you know, if a book has, we'll say has 200 pages, what do we predict its width to be? Okay, and so to answer this, we would plug in 200 into pages. So I'm going to just write width hat. So the predicted width is equal to 6.22 plus 0.0366 times, pages. We're going to plug in the value 200. So I got 6.22 plus 0.0366 times 200, and the number I get, 13.54. Okay, so our predicted width is 13.54 millimeters. Okay, so we predict a book with 200 pages will have a width of 13.54 millimeters. Is that good? Okay, let me just copy this regression equation over. So we've got predicted width is equal to 6.22 plus 0.0366 times pages, and we said for the width hat, predicted width is equal to 13.54 when pages equals 200. Okay? All right, give me the predicted width when pages equals 300. And also give me the predicted width when pages equals 400. Okay, so go ahead and do that. Take a minute to figure these out. All right, let's see how to do this. I'm going to just 6.22 plus 0.0366 times 300. We plug that in, and I get 17.2. And then this last one, plug in 400, and I get 20.86. So far, so good? Okay. How much did our prediction increase between 200 and 300 pages? How much did it increase? It went up. What do we have to add? 3.66, okay. And how much did it increase when I went from 300 to 400 pages?
3.4.
Another 3.66, right? Okay, so if I said pages equals 500, what do we predict the width would be? What can I do? I can just add 3.66, right? All right, so this would give me 24.6 and 8, so 52, right? I think I did my addition there. So if I added 3.66, 24.52, or you know, we could plug it in the formula and we would get the same, 24.52. Okay, so what's going on there? Why am I just adding 3.66? Where's this 3.66 coming from? Yeah, it's our slope multiplied by 100 here, right? Because here I'm increasing the number of pages is going up by 100, and so our predictions increase by 100 times the slope. Okay, so I've increased the number of pages by 100. Okay, I increased the number of pages by 100, so the corresponding prediction goes up by 3.66, which is equal to the slope times 100, or 0.0366 times 100, which is 3.66. Do we see that? Okay. So this is where we're going to talk about the interpretation of the slope. What does it mean to have a slope of 0.0366? Interpretation of the slope, which is if we increase x by 1, our prediction for y, and it's important that we say our prediction. For y changes by the slope, by the amount of the slope. So we look at the number of pages. So if a book has 201 pages, then my predicted width would go from 13.54 to 13.54 plus 0.0366, okay? Because that would be adding one page to the book. Okay. Now, because a page is so thin, it's hard to kind of appreciate the value of adding one page to the book, changing the thickness. I mean, we can imagine it, okay? It's easy for us to picture. But, you know, as far as value numbers go, we can talk about, okay, what happens if I add 100 pages? So I can look at, you know, find 100 pages in my textbook here, okay? And I can look at how thick 100 pages in the textbook is, and this width, maybe it's about 3.66 millimeters here, okay? And so we can say, if I increase x by 100, our prediction for y changes by the amount of the slope times 100, right? Okay, or if I increase x by, you know, 10, our prediction for y would increase by the amount of the slope times 10, okay? So this is the interpretation of the slope. Does that make sense? Okay. So so this is a good, I'm going to put a star here because this is important. You'll see a question about the interpretation of the slope on next week's quiz. Here, actually, let me just flip back and say just a couple more things about that. And I have to say prediction because we could have two different books, and one book could be 100 pages longer than the other book, but that book is not necessarily exactly 3.66 millimeters more than the other book. So it's not that, you know, if we compared two books, we would know exactly how much the width has changed. All we're saying is that our prediction, which is kind of based on the overall trend and relationship between the number of pages and its width, our prediction would change, okay? But it doesn't necessarily mean that if I have a 300-page book over here and a 400-page book over here, that this book, the 400-page book, is definitely 3.66 millimeters more, okay? It might be even wider, it might be less wide, who knows, okay? But overall, looking at the overall relationship between all the books, we would predict y would increase by the amount of the slope, okay? All right, let's talk about the intercept, okay? So in our case, the intercept is 6.22 millimeters, okay? Okay. The intercept is our prediction for y. If we could plug in 0 for x. Yeah, question.
So at the beginning when we did y hat, since a is now predicted, does it also get a hat, or does that just not mean?
We can say predicted width, or we could say width is with hat. Okay.
No, but like, will the a, since a is being predicted now, will that get a hat too, or?
No. We don't put a hat over 6.22 or anything like that. It's okay. Just and we don't put a hat over the a. A is just our intercept. Okay. So the intercept is our prediction for y if we could plug in 0 for x. Okay. So in some cases it makes sense to plug in 0 for x. In other cases it does not make sense to plug in 0 for x. Okay. Okay, so, you know, can we imagine a book with 0 pages? Maybe, maybe not. We could imagine tearing out all the pages in a book and we would be left with the cover. Okay, and so, you know, how thick is a book? with no pages, but just the covers, our prediction would be 6.22 millimeters. It kind of makes sense, okay? So this would be, you know, so in our case, we would say 6.22 is our prediction for a book with 0 pages. So maybe roughly the cover width. Okay. Let me see if there's an example I can find. Where, I don't know, maybe we want to predict someone's weight based on their height. Okay, so example where it does not make sense to plug in so maybe we have, you know, we'll say weight. It is interesting how weight is spelled just like height, but they definitely make different noises, right? Or different vowel sounds. Okay, so, you know, we're trying to predict weight based on height. Okay, and in this case, whatever A is, A would be our intercept. And it would be our prediction for someone's weight if their height was 0. Okay, but you can't have a person with height 0. Okay. Okay, that doesn't make sense, okay? So in this case, the interpretation of the height, not interpretation of the interpretation of the intercept does not make sense, okay? It's our prediction for someone's weight if their height were 0, or it's our prediction for y if x were 0, or if we plugged in x for 0, but you can't have a height of 0. That person does not exist in a literal sense. Okay. Good? Yes, question?
So what does that mean? Does that mean you can't regress that particular set of variables?
No, it's just plug in a reasonable value for x, and then you can predict the weight, okay? But that's what we have here. Okay. All right, let me, the idea behind the slope and the intercept, okay, so picking, or I should say finding, the slope and intercept. Okay, so we have this concept of a residual. The residual is the difference between the actual value and the predicted value. So small residuals mean your line did a good job of predicting it, and large residuals mean your line did not do a good job of predicting that value, okay? So, you know, what a residual looks like is you'd have some, maybe some data points. Okay, and the residual would be the difference between each, kind of the vertical difference between each dot and the line. Because basically what we're saying is that, you know, for this x, we predicted here, and the actual value was down here, okay? We predict the value is where the line is. We predict the values on the red line, and the actual value is down here. Okay, so our residual is equal to the actual minus the predicted. Okay. The slope and the intercept, the best fit line, is chosen to minimize the total of the residuals squared. Okay, so you know, you don't have to worry about trying to minimize the squared residuals because we actually have formulas for the slope and the intercept. Okay, so the slope, what letter is our slope? Right, so our slope is b, okay? And the calculation for the slope is r. What is r? Correlation coefficient, or just correlation, times sy over sx. What is sy? What is s without the y? Yeah, s is standard deviation. Sy is standard deviation of the y variable. Sx is standard deviation of the x variable, okay? So r is correlation. Sy is standard deviation of y variable. And Sx, standard deviation of x. Okay, so that's the slope. So the best fit line, because other people have done the calculations for us, will always have this formula. The correlation times standard deviation of y divided by standard deviation of x. Can I flip to the next slide, or are you guys still writing? Okay. All right, and so again, the slope, I'll just rewrite that, you don't have to rewrite it, is going to be, oops, slope is b r times sy over sx. Okay, and the intercept, what letter is the intercept? A, okay. The intercept is equal to y bar minus b times x bar. Okay, you have to find b first, okay? Must find the slope b first. Okay. And so what we have here is that because the intercept is this, the best fit line always runs through the point it's okay, x bar and y bar. Okay, the best fit line always runs through the point x bar, y bar. Okay, and that will be, and that's how we choose the intercept. That's how it's calculated. All right, is that good? Good with everybody? All right, we have a few warnings about using linear regression. So warnings and cautions. So these are like the things you should not do. Okay. So number one, or I mean, maybe I should say these are things you should be aware of. Okay. Linear regression only makes sense if the relationship is linear. Okay. And how do we tell if something is linear? Yeah, we must make a scatter plot, okay? So you must make a scatter plot to decide if something is linear. All right. R, just knowing R does not tell you if it's linear, okay? Okay. The only exception is if R is exactly 1 or R is exactly -1, then it's linear. But other than that, R could be 0.99 and it's not necessarily linear. Correlation is not causation, that's another thing. We've already talked about that, but it's worth writing again. Correlation is not causation. Oftentimes it can point us in the direction of finding causal relationships. Okay, correlation can help us decide or help us find causal relationships. This is causal, not casual. So causal being a cause and effect relationship. Okay, but deciding if something is a cause and effect requires knowledge of kind of the mechanisms at play, okay? Determining cause and effect all right, either requires maybe an experiment, requires a controlled experiment, an understanding of the kind of the inner workings of whatever we're talking about. Okay, so we might find I don't know. We might find people who couples who go on many dates in a month have overall higher satisfaction ratings of their relationship. Maybe we find that. Okay, does that mean more dates is causing higher satisfaction? Maybe, maybe not. It could also be that because it's higher satisfaction, they're choosing to go on more dates. Okay, we don't know which one is causing the other. Okay, and so we would have to do some kind of controlled experiment, which would be difficult to do when it regards relationships, because I don't know, it's complicated. Or we would need to understand the inner workings of the human mind when it comes to relationships, and that's also a great mystery as well. So it's hard, a lot of these things, you'll see stuff published where it'll say like, studies have shown this and this, and it's like, oh, well, I guess that means I should start doing this. Maybe, maybe not, okay? Correlation is not necessarily causation, okay? It can help, but not always, okay? The next one is worth its own, a new kind of theme. Okay, watch out for outliers. They can really mess things up, okay? Okay, they can mess up your analysis. Okay, let's say we want to know, is there a relationship between shoe size and shoe size and wealth, okay? Is there a relationship between shoe size and wealth? Okay, and what do we expect our answer to be? No, right? We would expect no correlation. Okay, so we would see, we'd look at people, and you have people with big feet, people with small feet. Big feet, people with big feet have some, lots of money. People with big feet have little money. People with small feet have lots of money. So we'd see something like this, okay? Let's say somehow in your data set, Shaquille O'Neal ended up in your data set, okay? So Shaq would have very big feet, and he's also very wealthy, right? So suddenly, without Shaquille O'Neal, we would see, basically no trend, right? So we'd see no trend. Okay, and now we're gonna throw in Shaq, and he's gonna be out here, okay? And then what's gonna happen? Our trend is now we're gonna suddenly see some kind of trend like this. And our analysis will say, oh, bigger feet, more wealth, okay? Yes?
So we only need one outlier to make another line?
One outlier can mess things up, okay? Depending, okay? It depends where the outlier is, but one outlier could just throw everything off. It's possible, okay? Okay, so yeah, depending on the outlier, one outlier could just totally throw it off. Depending on the data, one outlier could throw off the entire analysis. So, how do you decide if something's an outlier?
If it's not close.
Yeah, well, you have to create a scatter plot, okay? So this is like our answer to everything. You got to make a scatter plot and look, okay? And if you see a data point that's like way out there all by itself, you have to say, well, should this data point be included in my analysis, okay? And so you probably want to say, well, Shaq is atypical, is not like most other people, so I'm not going to include him in my analysis, okay? And then you could say for everyone else, is there a relationship between shoe size and wealth? And we'd see no correlation, okay? And maybe, if we looked at the entire population, maybe we'd see that, there are a lot of, I don't know, professional athletes that have very big feet and make a lot of money, but then, you'd also have a lot of people with small feet that make a lot of money too. So it's gonna be hard. So depending on your data, if you have one outlier, it could really throw things off. So graph your data, check to see if there's outliers. Okay. Okay, and then the other one that you don't want to do is do not extrapolate. Or in other words, do not make predictions where you do not have data. Okay, so here's a silly example. Okay, let's say you have a child, or maybe someone with a young child. Okay, and you're going to look at the child's age, and you're going to look at the child's height. Okay, and so maybe starting at age 2 or 3, you start measuring the kid's height, and every year or every month, it seems like the kid. Let me actually make this more pronounced. Okay, so it seems over the course of time, the kid is growing every something like that. Okay, so between ages 3 through age 12, okay, the kid has grown every single year. Okay, kid has grown every single year, and so you might say, oh, well, at this rate, by the time the kid is by the time this person grows up to 70 years old, he's going to be I don't know, 25 feet tall or something like that. Okay, because you say every single year the kid has grown, I don't know, half an inch or something like that. Okay, and that would be a very silly thing to do, right? It'd be very silly to assume that this rate of growth will continue on, into adulthood. Okay, because we know that as people get older, the age levels off. You reach whatever, 18 years old, 20 years old, or some people younger, 14 or whatever, and you stop growing. Okay, you reach a certain height, and that's like the height for the rest of your life until you reach old age, when your bones start to deteriorate and you start to shrink in height. Okay, but so it would be silly to say, my child has grown every year between ages 3 to 12. So by age 60, he will be 30 feet tall. Okay, that would be dumb. But people do stuff like this all the time, right? They say, oh, for the past 30 years, we've seen I don't know, the crime rate go like this, or we've seen this thing, this phenomenon going, you know, for the past 20 years or whatever, okay? And then they say, okay, well, so by the year 2050, this is what's going to happen, okay? Or, you know, and the truth is no one knows what's going to happen in the future. Nobody has collected data from the future, so we have no idea what things will look like. That prediction could be correct, that prediction could be super wrong, okay? So, I'll draw, you know, little pictures over here. You know, we could see something like this. This is where we've collected data up to here. But as far as the future goes, the future could go like this, it could go like that, it could go like that, you know, it could even go like that. Who knows? Nobody knows what will happen where we haven't collected data. And same for, you know, traveling back in time, okay? We can say, all right, we've collected this data for the past 30 years, and so, you know, we want to know what life was like back in the 1700s, okay? So, if we go back in time, this is what things might have looked like, okay? That would also be a very silly thing to do, okay? And I think people don't often extrapolate into the past because we realize how ridiculous some of these things would be, because we would know, like, oh, things didn't look like that way, you know, in the 1700s. But people do stuff like this for the future, and so who knows, okay? So anyway, that's, so don't extrapolate, okay? Linear regression is useful, and you can say, if the current trend continues on into the future, we can expect things to look like this. That would be acceptable, but that's also a big if, right? If the current trend continues, then yes, things might look this way. But again, that is if things continue in the same trend, which may or may not be reasonable. Is that okay? All right, great. Okay, and the last topic here is we have something called R squared. This is called the coefficient of determination. Okay, and you know, for linear regression, you take R, little r squared is equal to big R squared, okay? For linear regression. For other forms of regression, this is not always the case. And so because of this, R squared will always be between 0 and 1. Okay? And the meaning of R squared is it tells us the amount of variation in y that can be explained by the variation in x. Okay, so let me just write that down. Okay, so what does that mean? Well, maybe we want to look at the relationship between someone's height and someone's weight. Okay, and we create some kind of scatter plot, and we calculate correlation. Maybe we get R is equal to 0.6. Okay, I'm just making this up. Okay, so what is R squared? R squared would be 0.6 squared, and that would be 0.36. Okay, so what this means is we can say, you know, what goes into determining someone's weight? okay? So what are the different things that go into determining someone's weight, okay? You have things like the person's height factors into someone's weight, but also kind of, you know, maybe their waist size, maybe their muscle to body fat ratio, maybe their bone density, maybe, you know, all sorts of different things. There's a bunch of different aspects that factor into how much a person can weigh, right? And so what goes into determining someone's weight? Well, what we're saying is that if we know someone's height, that accounts for about 36% of the person's weight, okay? Everything else, the other 64%, is determined by the other things that we haven't recorded. Things like waist size and, I don't know, these other factors, okay? So we're saying what goes into determining someone's weight? So we can say height can explain or account for 36% of someone's weight. The other 64% are other factors. So maybe waist size, muscle fat ratio, I don't know, other things, okay? Whatever else it might be, diet, stuff like that, okay? And that's what we have. Okay, we'll end there, and we'll see you guys next week. Have a good week.